Okay, so now we're starting section 8.3, where we're going to be looking at testing the differences between means, but with dependent or paired samples. To perform a t-test, we have to have paired data. And the first, we're going to look at a couple different things in here. To perform a two-sample hypothesis test for paired samples, we'll be looking at the differences between each data pair. So that we're going to find the difference between sample 1 minus sample 2 of the same for each data pair. And we calculate these differences. From that, we're going to add up these individual differences, divide by the number of pairs, and that's going to give us what's known as the D bar, or the mean of the differences of the pairs. The conditions that are required are this: two samples must be randomly selected, they must be dependent or paired, and both populations must be normally distributed. And if this is the case, then this approximates a t-distribution with n minus 1, where n is the number of pairs, degrees of freedom. So here are some of the symbols that we're going to use. N will stand for the number of pairs of data. D is the difference between each entry. Entry 1 for sample 1 minus entry 1 of sample 2. And then mu sub D is the hypothesized mean. Usually, we're going to be looking at this being equal to 0, or less than 0, or greater than 0. The D bar is the sum of the individual differences divided by the number of pairs. And we have the standard deviation of the differences, which is, this formula here is just a little easier to put into your calculator. We're going to set up a table to come up with these values, and I'll show you that in just a minute. So the test statistic is D bar, which is the sum of the differences divided by the number of pairs. And the standardized test statistic is T is equal to D bar, this quantity up here, minus mu sub D, which is usually 0, so we don't really subtract anything, divided by the standard deviation of the differences, which we saw that formula on the previous slide, and that quantity there is divided by the square root of the sample size. And degrees of freedom is always the number of pairs minus 1. So to do the hypotheses, it's pretty similar to what we've always done. We state the hypotheses, we identify the significance level, we identify the degrees of freedom. In this case, it's the number of pairs minus 1. Determine the critical values from table 5, our t-distribution table. Then we determine the rejection regions using that critical value and the alternative hypothesis. We do these calculations, and then we find the standardized test statistics. See, we put all of these into this value here is put here. This is minus 0. This value here is put right here, divided by the square root of the sample size. We make a decision. If T is in the rejection region, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And then we interpret it. So let's look at an example. Now remember, our data is paired. So we have 8 athletes, and we looked at their vertical jump before and after using these new special strength shoes. So if we're going to do the height before minus the height after, and so if they jump higher, remember this value should be negative. So our hypothesis is that the mu sub D would be negative or less than 0, because the jump in sample 2 will be higher. So a small number minus a bigger number will always be negative. So in this case, we're dealing with a mu sub D less than 0. That makes this a left-tailed, one-tailed test. The significance level is 10% given in the problem, and our degrees of freedom is the number of pairs. We had 8 athletes, minus 1, which is 7. We use the degrees of freedom and table 5 to determine that our critical value is negative 1.415. And the rejection region, because this is a left-tailed test, is everything smaller than negative 1.415. Now we need to calculate the test statistic. The easiest way to do this is to set the before height jump, and then the next column is after sample 2's data, after they use the strength shoes. Then we calculate the difference. 24 minus 26 is negative 2. 22 minus 25 is negative 3. 25 minus 25 is 0. Then we have then we're going to do another column where we're going to square these differences. Negative 2 squared is 4. Negative 3 squared is 9. 0 squared is 0. Negative 1 squared is positive 1, and so forth. Then we sum up these two columns, and we're going to put them into our formula. Remember, D bar is the sum of the differences divided by the number of pairs. So this column summed up is negative 14, divided by the 8 pairs is negative 1.75. The standard deviation is the sum of the d squareds, which, remember, if we sum up this column, we got 56, so it's 56 minus the sum of this column, the negative 14, quantity squared divided by the number of pairs, and that's divided by 8 minus 1. This value comes out to be 2.1213. We then put this into our test statistic, which is d bar, which we saw on the previous slide was negative 1.75, minus mu sub d, which I told you is always 0. Then the standard deviation we calculated on the previous slide was 2.1213, and that quantity is divided by the square root of the number of pairs, or the square root of 8. This is approximately negative 2.333. This is our test statistic. The test statistic does fall into our rejection region, so we reject the null hypothesis and say, at the 10% level of significance, there is enough evidence to support the shoe manufacturer's claim that the athletes did increase their vertical jump heights after using their strength shoes. That's the end of section 8.3. That's all we're going to be doing in chapter 8. We won't be doing 8.4. And so, well, we won't be doing 8. This is all we're going to do in section 8.3. In some terms, we may do 8.4. We will perform a t-test. We can now perform a t-test to test the mean of the differences for the population of paired data.